Thank you. So I will present the work done in close cooperation with Daniel Asmus and Konrad Tristan. Um, so Many thanks to Leo and Almudena, who did a very nice introduction of the topic, so I can fully skip these introductory slides. I just hope that you remember the most important points, which is then when we started resolving these mid-infrared structures in AGN, we saw, well, first with VLTI MIDI, so on the parsec scales, and then with VISIR on larger scales. What we saw is that they appear elongated along the polar direction of the along the polar directions of the AGN axis, which is quite opposite from the classical torus, which you would expect to appear elongated in the equatorial direction. So the question now is, what is causing this apparent polar elongation? So could it be maybe when we are talking about small scales, simply just some projection effect? So if we are seeing the slightly inclined torus, so we are seeing that hot inner funnel, which in projection appears elongated in the polar direction. Or when we talk about larger scales, could it be that we are seeing just some diffused dust in the host galaxy, which is being illuminated by the accretion disk and collimated by the compact torus. So again, we get this appearance of the polar elongation. Or as Sebastian Huning suggested a few years ago, that instead of a torus, we have a rather thin disk, which is then being puffed up at the inner rim, so at dust sublimation radius by the accretion disk radiation pressure, which is then taking the material further out and making this kind of a hollow dusty cone. Maybe I can just quickly reflect on the issue raised at the end of the previous session. So in some way, this is a matter of semantics, like what you call a disk and what you call a torus, right? A torus is a thick disk, a disk is a thin torus. Or you could call this a puffed up inner rim of a disk, or you could still say, well, here is a torus, but just much more compact. And well, in some way, all of this would be correct. But for me, the term torus is I think it's causing a wrong picture, because when you say a torus, you had this kind of monolithic donut, which is just sitting there and doing nothing. Which, as Leo pointed out, it's difficult really to sustain the height of such structure on the long term. You would expect it to collapse into a disk. So you really need something that is actively keeping the height. And this is where this radiation pressure naturally comes into play. And then, of course, depending on the conditions, you could launch a wind to the larger scales, or the material could fall back and form something that resembles a torus. So I think it's important to have in mind that this is really the obscuration is like really this dynamic region, right? Okay. So to really test these ideas, as Leo also pointed out, we really have, it comes down to the two sources, so AGN in Circinus and NGC 1068 galaxies, which are the brightest, nearest and brightest in mid-infrared of the obscured AGN. And this was just a slide for, these objects are very well known in the AGN community, but this was just for the outsiders to illustrate. So here I'm showing a snapshot of the conference program on AGN obscuration held in Chile 2 years ago. You can see these two sources appeared in more than a dozen of talk titles. So basically, every time you have a new model, a code, or new instruments, you would go first to these sources, because in many ways they form our view of how the obscured AGN looked like. And as you already heard, both of them turned out to appear different than expected. So in the remaining of the talk, I will focus on AGN in Circinus galaxy. So here on the left, you already seen this is like a simple surface brightness reconstruction. And again, so this component here along the polar direction. So here we have the ionization cone and the Ward-Maser disk. So what was found that in mid-infrared, this component along the polar elongation contributes to 80% of the flux on the scales of the few parsecs. So only about 20% goes to this equatorial component. Then looking at the same source with the VISIR. So here we're talking about the scales of few tens of parsecs. we see this elongated bar-like feature, which was originally detected by Chris Peckham et al. With Gemini South, but now seen much more detail, much better with VISIR. So here we have archival images at 10 and 18 microns, and then at 8 and 12 microns, the images we obtained in science verification with the upgraded VISIR in 2016. And in the bottom row is after PSF subtraction, where you can still see some residuals, but you can see this clear elongated bar. Okay, so this is the same image at 12 microns, just in inverted colors. And then if you would zoom inside with VLTI MIDI, I hope you can make out here on the top right. So you see the two disc-like components corresponding to these two surface brightness dilution models. Then in red line is showing the warp maser disk. And here on the bottom left in the grayscale, you see the ionization cone visible in optical. And then what we noted, like if you would overplot ionization cone of the VISIR image, so the blue lines, dashed lines are delineating its edges. So this bar is exactly aligned with the edge of the cone. So we thought it cannot be a coincidence. We said, what if the ionization cone is enveloped, or if it's mixed with the low density dust, so that the surface brightness of the dust would be low and it would be lost in the PSF and background noise, but you would have this edge brightening effect. And then if you note that if you put there tilted accretion disks in the tropic emission pattern, you would expect to get to see only brightly only one edge and not the other, as we see in this temperature profile here, which I obtained with the Monte Carlo ready transfer simulations with the skirt code. And here in the top row, so you see the images of the ready transfer model, these for wavelengths. And in the second row are synthetic observations of the model, so how the model would be looked, observed by VISIR, which is basically convolution with the PSF model with a few other tricks. And now you can see that it's quite good match to the morphology of the observed images. And here we are comparing, sorry?
Short minute.
How much? I didn't hear you.
1 minute.
Okay. Oh. So here we are showing the comparison of the model SED to the photometry and spectra we compiled from the literature. So quite good match there. Here we also extracted photometry from different apertures along the bar and perpendicular for it, and we also got quite good match, except here at the outer edges where we are dominated by the noise and PSF. We also tested if the classical torus and the sphere model could work, and it doesn't, but I have to skip through that. So now looking at the MIDI data, so starting from the MIDI model and after some modifications, so we came down to this final model, so very thin disk and polar outflow shaped like hyperboloid. And in the top row, we have the model images. The next row is, again, synthetic observations, basically Fourier transform. The third row, we compare the correlated fluxes at different position angles with our models, and you can see they match quite well. Here we have the comparison of the spectra, full spectra, and along other position angles, getting quite good match there. So this is just a nice illustration of the model. So made by mapping these three images at 8, 10, and 30 microns to blue, red, and green channels into a single picture. So we have a thin disk, slightly tilted towards us, and this hollow cone-like outflow actually shaped like hyperboloid. And here I will just point out that recent work by Medansi et al., who did like this semi-analytical model of dusty gas clouds in the gravity field of a black hole, with subcircular rotation and radiation pressure. And when they plugged in the values of integration NH of Circinus, they basically obtained the structure, which is remarkably similar to what we got. So instead of conclusions, this is the geometry of the dust that we propose as a prototype for this new population of dust AGN with the polar dusty winds. So thank you.
Okay, thank you. There is no question in the Slack.